In the next section, we'll finally apply the concentration bounds, mostly the Chernoff bound, to some concrete algorithms, both to show you that it's useful and to see how they are used. I might try to go a little quicker over this. There's past recordings where this is done in maybe more excessive detail. The first application is our standard strategy to boost the success probability for Monte Carlo algorithms. Said already, if you're not happy with an algorithm that's wrong half the time, you just repeat it several times and take whatever the majority vote gave you. And we can even be more cautious. If there is no clear majority, we say we failed. So here is that formally written up. You do t independent runs of your Monte Carlo algorithm on the same input x, but with fresh independent random bits. If at least t half rounded up, many runs yield the same result, then we output that. I guess we always pick an odd t, so just that there's no ties. And otherwise we give up. So how good is this? And it turns out that depends on the exact type of the Monte Carlo algorithm we have. Here we look at bounded error Monte Carlo. So in particular, if you remember the definition, this meant that the probability that this algorithm A on an input X is the correct output. This has to be at least 1/2 plus some epsilon. And this epsilon must be independent of the input that we pick. There's an absolute constant depending only on the algorithm, so that we can bound the success probability away from 1/2. That was bounded error. And now we're saying if we have such an algorithm, whatever the exact epsilon for this algorithm is, we can make it with high probability. So essentially make epsilon subpolynomial, shrinking like 1 over a super polynomial function. Little o of n to the minus c for all constant c, by just a moderate number of repetitions, slightly more than logarithmic. So let's see how to prove that. The goal will eventually be to use the Chernoff bound, so let's keep that handy. Might have to make this a little smaller in the end. We'll see. So the goal is to do something where you can apply the binomial Chernoff bound. So we need to somehow generate a binomial distribution. For all intents and purposes, you can assume that t is log squared. This is just for you to keep in mind. It would actually be good enough to take log n times log n or whatever else small growth above log n. But that's kind of morally the idea that you should keep in mind. So we do t repetitions. That means we can define t random variables, x1, x2 up to xt, where xi is the event for the random variable that the ith run succeeds, which means produces the right output. Right, so on our input x, we actually get what the function is supposed to output. And so this is an indicator random variable of this event that the ith run satisfies this. And of course, this is a 0, 1 variable. So it has some probability to occur. And we actually know a bound for this probability. Now, because we pick the same x, we don't know exactly what p is, but we pick the same x and we do independent repetitions. So really these the sequence is IID, independent and identically distributed. And it has some Bernoulli p probability or Bernoulli p distribution for each xi. We just don't know the p exactly. We know a lower bound, but we can pretend that it is known exactly. Then the algorithm will only be more likely to succeed. That makes the calculations a little easier if you don't have to have another inequality flying around. So we'll assume that we have exactly 1/2 plus epsilon for some constant epsilon greater 0. Now, if you define x by summing up all those indicator random variables, we get something that's a binomial distribution by definition. T repetitions, each event occurs with probability p. So what's the sense of doing that? Well, we can now express that our overall algorithm succeeds, or rather that it fails, say. The majority vote fails if and only if we have not enough summands summing to 1. So if and only if x is too small. Yeah. Let's always assume that t is an odd number just to avoid kind of stupid corner cases. I don't think that adds any interesting twists to it. Okay, now we're essentially in business. We have reformulated our algorithmic problem as a purely statistical one. What's the probability that a certain binomial is at most that value? And so let's calculate the probability for that to happen. The probability that x is less than, let's be very strict, so oh, come on. I'm making the event less likely. That makes the more likely. I'm making the condition weaker by dropping the floors. So that is a more likely event, which means the probability can only go up. And now we have to rewrite that in a form that matches the Chernoff bound. Maybe we can afford that on this page a bit bigger. The point is we need to rewrite it so that it matches that form. So we have to subtract the expected value and it turns out it's more convenient to flip it around and add p on both sides. So we do a whole rearrangement. Okay, let me first write it down. So what have we done? I added p on both sides. Well, we divided by t first. Then we have x divided t less or equal 1/2. Then multiply that by -1. Then you have minus x over t greater or equal -1/2, and then we add p. So that's the same inequality, just rewritten. And so that's close to what we need. This is the wrong way around, but we'll take absolute values. But this expresses that essentially our random variable is much smaller than the average. That's half of the tails that we bound with the Chernoff bound. So we make the event again more likely by including both options being way too small or way too big. And so formally we express that as the absolute value to be greater than what we have, p minus 1/2. And so that's now in the form that we need for Chernov's bound. In particular, this p minus 1/2 is exactly our epsilon, which is greater than 0, so that matches. It's called delta in the bound, but it's other than that the same. So here we applied Chernoff bound. And we have to insert what we have on the other side. So it's 2e to the minus. Then we have delta squared, which is epsilon squared in our case. And the n is a t because our binomial has t repetitions. Okay. So far, so good. That's the probability that t repetitions fail. Now, we're claiming that this is not happening. With high probability, this isn't happening. And so if you remember what that means, for every exponent c, we have to show that the probability is in this little o of n to the minus c. So we're given such a c, and we compute n to the c times the probability that this algorithm fails. If that goes to 0, then we've proven the little o of bound. Majority vote fails. So we claim that this goes to 0, and from this we would follow that the probability that this fails is in little o of n to the minus c. Because c was arbitrary, that implies that the algorithm doesn't fail. With high probability. Now we still have to show that this convergence here is true. But that's not actually that hard. Using our bound from above, we can, let me copy it once. So we take this, we use our bound from above, this one. And I'm going to put the n to the c into the exponent. So everything is within an exp. And then I have c times natural log of n. And we have the minus 2 epsilon squared t. And at this point, we have to use what we know about t, namely that it is a super polynomial. Which means we have some constant times log n minus another constant times something that grows much stronger than log n. So that means the overall thing in the exponent goes to minus infinity because the second part dominates. The t grows bigger. So the exponent goes to minus infinity, which means the exponential is going to 0. And that's what we claimed. So this is prototypical of the type of with high probability proofs. We apply Chernoff bound. The creativity goes into how to define the xi. Here's was very simple because we just repeat the same thing several times. Then we reformulate what fails means in terms of bounding a binomial. And again, the magic is majority means exactly t½ is our threshold, but the success probability is slightly bigger than 1/2. So there will be, when n gets bigger and bigger, there will be a linear difference between t½ and the expectation t times p. And that's what we use here. So in this case, you get this exponential upper bound. Then the second step is also always the same. If you show with high probability, you have this n to the c factor that you're supposed to dominate. Or the probability is supposed to go to 0 faster than this n to the minus c. And so you multiply this together, put it in the exponent, and make sure that the exponent goes to negative infinity. Okay. This was nice to finish off this part about majority voting. Let's drive home the point that really unbounded error is pretty much different. So the formal statement here says, okay, you can still do majority vote, of course, but there is an example where you have an unbounded error Monte Carlo algorithm that even has a restriction. It uses a linear number of bits. It could use polynomially many, but here, say, it only uses a linear number. And then we can say, we can guarantee that the majority votes even to reach a certain fixed probability. We don't even aim for high probability bound, requires already super polynomially many repetitions. So there's no way to turn an unbounded error Monte Carlo algorithm into a bounded error Monte Carlo algorithm while keeping the running time polynomial. We're basically just showing here that the trivial way to do it fails. It's not actually supporting my statement, but we'll come back to that in the next unit. We start with essentially the same kind of setup. So all we know is that the success probability now is strictly greater than 1/2, with no bound. And for sake of the argument, again, I guess we can say that the number of random bits is exactly n. You'll see this doesn't really change anything. But at least in the worst case, A now has a different run for every random input. So here it would be 2 to the n different runs for the same input, depending on the random bits. And of course, these are equally likely the way we define things. So each has probability of being chosen 2 to the minus n. Okay. That means we can follow the same approach as above. To get that the majority vote fails if a random variable x is less or equal to half t half. And again, x is a binomial distribution, but this time all we can say is that the probability here, p, is strictly greater than 1/2. But we can say a little bit more under this assumption, because remember, the probabilistic Turing machine, everything is deterministic once the random bits are chosen. And if I only have 2 to the n different runs, and it has to be strictly greater than 1/2, we actually know it could be 1/2 to the plus 2 to the minus n in the worst case. Like it has to be at least that big. And let's suppose that we pick an algorithm where this is indeed the worst case that happens. So in reality, the bound on the probability is not completely unknown, because the number of different runs is not completely unknown and unbounded. It depends on the number of random bits that you use. You can still make some statement about the probability. But the key thing here is that this epsilon is going to 0 and even exponentially small. So we maybe smell the trouble there. Okay. Now the rest is a bit of rote calculation. There's one step which may be worth doing. So maybe let me try to give the argument. First of all, we show that now if we take our x and we try to get into the range t half and the expected value of x, this is actually very unlikely. That's again going to use Chernoff bounds. So what does that mean? If the number of equal outcomes is a majority, but below the expected value, we shouldn't expect it to be much larger than the expected value. So this is the range where the majority vote succeeds, right? But unfortunately, this is this needs this is actually not yeah, you want this probability to not be so I guess it's one part of where we have success if x is larger than the expected value. Will also succeed, but this range is not very likely because the binomial distribution is symmetric. The probability to fall above the expected value is exactly 1/2. We only need an upper bound. So from these two things, the probability that the majority vote overall fails is again the probability that our x is too small, less than t half, and that is at least as much as the probability that t is strictly less than t half, okay? And we'll use that to rewrite for the two parts. So there's if you think about the whole range that x could take, there's t half here in the middle. And then the expected value is slightly bigger. It's a tiny bit to the right. The range where we succeed is this green part. Sorry, x is greater than t half. That's the green. That's where our majority vote is happy and succeeds. And so the probability that it fails is the converse probability, and we express that by taking the probability to be below the expected value and subtract the probability for the part in between. Yep. So that's this tiny bit here is that blue part. And so we know this is at least 1/2. It's essentially 1/2. sorry, this should be greater or equal. And if the random variable is symmetric, you have exactly the same mass left and right of the expected value, but because it's discrete, the expected value itself could have non-zero probability. So it's half plus the probability to hit exactly E of x. But what we need is an upper bound here, so that's right. And what we subtract is an upper bound on this thing, so what we subtract then turns into a lower bound. So we have this epsilon t 3 to the epsilon t. And we'll see that this essentially converges to 1/2. So it's not going to be that's what we want to show. If it was to converge to something, well, that's the probability that it fails. And if we can show that this converges to 1/2 unless you pick an absurd large t. So suppose we pick a polynomial number of repetitions. And recall the epsilon was this 1/2 to the minus n. Then what do we get? To the minus n, n to the c, 3 to the 2 to the minus n, n to the c. So essentially this part is going, that the exponent is going to 0 very quickly. So the exponent part is going to 1. This n to the c is fighting against an exponential, so the exponential wins and the whole thing goes to 0. So what does that mean? If we do any polynomial number of repetitions, the majority vote fails with the probability that converges to 1/2. In particular, it is below any kind of delta or any delta greater 1/2 for a sufficiently large n. And so no polynomial number of repetitions suffices, right? Okay, what we still have to show is this claim up here. I should say we will show. And so that's this blue bit. Probability that x lies in the range between t/2 and its expected value less or equal epsilon t 3 to the epsilon t, right? Yep. This is not something where you can use Chernoff bounds. So there, the easiest argument I found was essentially going by the definition. So we take this, take this guy, just plug in what we know about that. It's a binomial distribution, so we know what the probability weights are like. And okay, let me try to write this a bit cleanly. The values for x range from the lower bound, so t/2 excluded, so let's say t/2 plus 1, up to the expected value is p times t, but we know what p is. That's half plus epsilon. So we have t half plus epsilon t here. There's a plus minus rounding issue here that I'm trying to sweep under the rug to not make the calculation uglier than needed. And what's the probability for a binomial to have a certain value I? It's the binomial coefficient, and then this I times the success probability, and the counter probability for the other attempts. All right, so that's just the probability that binomial, again, remember x is a binomial with parameters t and p. And so that's just the probability that x has this value t, I, sorry. And so we're going to bound this a bit. And it turns out you can be relatively generous in how you bound it and still get this upper bound. What's this pen doing? So first, let's leave the sum aside. The binomial coefficient so this whole probability has a certain shape. It goes up and then goes down again, so it has a peak at the expected value. If you plot that as a function, this gray thing. And so we can upper bound the sum by replacing all summands by the largest summand. Okay. And so we'll do, I think one step further would make sense here. We're summing from t half to something larger, so the largest is actually the first summand. But, just plug that in. Then we have 1/2 plus epsilon to the t half, 1/2 minus epsilon to the t half. So largest summand. And you can upper bound this binomial coefficient. If you think about it, so it's a set of, we're picking from t elements, t half elements. That's effectively, it's effectively like a bit vector of size t, where you know half of the bits are 1. But certainly this binomial is upper bounded by 2 to the t. So let's just use that here, that this is at most 2 to the t. That's a generous upper bound, actually, but doesn't hurt. And if we want, we can write that as 4 to the t half. Turns out that's convenient, so we can now rewrite. The trick that with changing the sum is that now all summands are the same, so I just get the number of summands, which is epsilon t, times the summands themselves. And there we have 4 to the t half, and then these guys all to the t half, so it's one big exponential. Half plus epsilon, half minus epsilon, and the whole thing to the power t half. So I wonder if I was too generous at that point. Okay, let's see. So this bit in the sum here, you can multiply this out. So it's 1 minus 4 epsilon squared. And you get a quarter from the 1/2 squared, and then minus epsilon squared, and the whole thing times 4. That's certainly less than 1, so you get that here. Then I only get an epsilon times t upper bound. I had an additional factor written down, but I'm not sure where to get that from. Let's see if we need this 3 to the epsilon t here, really, because it went to 1 anyways. Might simplify the argument a bit. So I'm gonna say this is not needed, so let me remove that bit. And that wouldn't change anything, it just makes this a bit easier. Maybe it's just that I was generous here. I think I was overly cautious back then, and upper bounded not the entire summand by the largest summand, but the individual parts. So this part is biggest for t-half, this part is biggest for the other extreme point for I, but I don't see why we would need that. So should be fine. And so the argument is slightly shorter. Again, the point is unbounded error is not good enough. We need an exponential number of repetitions. So that's an indication that this is not a suitable model. At this point, I thought it's useful to make a short comment on what happens with randomization in optimization algorithms. Because the majority vote that we've just discussed makes a lot of sense if you have a decision problem where there's only yes or no outputs. If you have an optimization problem, you could have a randomized algorithm that outputs any kind of feasible solution, but it need not necessarily be an optimal one. Then if that's the situation, why would you follow the majority vote if you can just compare from all the solutions you got which one was best? And so a natural approach for optimization problems would be not to do the majority vote, but just output the best solution you've ever seen in all the random trials. And then this is a natural thing to do. We'll have sometimes a hard time proving that this is doing any better than the majority vote. And we'll kind of reserve this for the approximation part. So for this chapter, we only allow the exact optimal solution. And then the whole theory is essentially equivalent to requiring that you have a majority vote. This doesn't seem to make a big difference. There's more to come. I just wanted to make this point here because if you think about randomized algorithms for, say, a vertex cover, and if any of the independent runs found a smaller vertex cover, why would you go with the majority vote? And obviously, you wouldn't. This is more to make the theory around for the decision problems. I have one last example where I'll only sketch the proof. and I'll refer you to some old recordings if you want to see the full details. What we've used so far is essentially the Chernoff bound in its very raw, plain vanilla form, because the majority vote does exactly identical repetitions, and that seems like an obvious fit for the Chernoff bound, but maybe this is not always as easy. And so there's an example where you can, with a trick, apply the Chernoff bound still, even though it's not obvious why there would be an independent repetition of things. And that's this statement about quicksort. So you'll remember what I mean by randomized quicksort here is that you pick a random pivot in each step. And the other thing we have to talk about is the recursion tree. What do I mean by that? The original input for quicksort is some array. And then you pick some pivot. We don't know up front where it will be, but after partitioning, I know maybe it lies here. That's my first pivot. And then I know these are less or equal, these are greater or equal than the pivot. I'll just write P. And I'm going to recurse on the two sides. And so I naturally get a tree from that, where this is the root, and then I have a vertex here or node here. And there will be some other pivot in this part, and maybe here as well. So I keep splitting this until the parts are tiny. And okay, if I draw this until the end, we're going to sit here for a while, so let me stop here. The thing is, on each level, if you sum up the effort on every level, you have linear costs for each of them as an upper bound. Maybe some levels are not empty, are partially empty. Let's do one more here, because some elements already are done, and so they don't have to participate any further. There's always a most linear. So you have a linear cost on each level. If you can bound the height of this tree, you get a bound for the overall number of comparisons. That's what the corollary says. If you can bound the height of this tree, then the number of comparisons follows. And so we're interested in the worst branch of this tree. Intuitively, you can say in each step you follow the bigger subproblem. But of course, that's only an expectation true. Really what you mean is the height of this tree, the longest path from the root to any leaf. So if we show that this is logarithmic, then we have shown that quicksort has order n log n cost, not only in expectation, but with high probability in our strong sense. That's the reason why you'll essentially never see quicksort fail in never go quadratic if it's properly randomized. Maybe let me be picky here, because the statement kind of hinges on the fact that you don't have duplicate keys, because then the randomization kind of fails. You have to play further tricks, but that's for a different time. I've written a long paper about exactly that and what happens. There's much more known, but this is not a lecture on quicksort. I want to sketch how you can apply Chernoff bounds to prove this logarithmic height statement. But I have to identify something that behaves like a binomial distribution. And maybe that's at first not obvious how that fits together. that's supposed to be a t. Where's the binomial distribution? We have to make it so that it appears. So a little bit of notation. Let's say V is any node in this recursion tree. And n of V is the number of elements there. So in my picture, I would have said this guy is called V, and n of V is the length of its range here. That's n of V. And let's call J of V the random number of elements in the left subtree, or left recursive call. Okay, so in this case, the J would be this, the size of the left child. The thing is, I want to focus on a single vertex for a single node for now. So I'm describing these quantities from the perspective of one vertex. Of course, J of V is always this n of V of the left child. That's clear, but I'm trying to make the point here. And now we say V is balanced if J of V divided n of V is in a good range, say between 3/4 and 1/4. So graphically, you want your pivot to fall in the middle range. And if it's too far, if it's in the outer half, the leftmost or the rightmost quarter, then you decide that that subtree somehow went wrong. Okay. But the point is, we don't care about individual failures. We just care about constantly failing. The key observation is if you have a recursion tree for n elements in the beginning, and you look at any path, then you cannot have arbitrarily many failure nodes which are unbalanced. So you cannot have arbitrarily many balanced nodes on this path. Namely, okay, the number you basically work out backwards and insert. But the idea is if you have a balanced node, you lose at least 1/4 of the elements, and you continue with 3/4. So the question is, how often do you have to multiply n by 3/4? So you start with n. The number of balanced nodes is how much this reduces. And you stop when you have a single vertex. So if you solve that for B, you get this, this quantity. Yeah, okay, I computed that this is 3 times 5 ln n. Probably won't need that because we don't do the full computation, I think. So you can only have so many balanced nodes before essentially the size of your tree reaches 1, and then you're at a leaf and you have to stop. The only way how your tree can grow arbitrarily tall is by having unbalanced nodes all the time. And so we're now almost there. We'll define our along any path. So we start at the root, and then we just follow an arbitrary path. And because the thing is symmetric, I'm going to just follow the left path, but the same statement applies in the end by a union bound over all paths. So the unquantitative statement is this. That's why we can focus on a single path. And we'll define indicator random variables that the ith node is balanced. And then you see that if you had a very long path, you would have many x's, but they sum to something much smaller than their expected value. So if we have x is the sum of many of these, say depth d, then that's, well, it's hopefully binomially distributed with some probability p, which will essentially be 1/2. That's how we picked it. We picked the balanced conditions so that it's equally likely to be balanced and unbalanced. And if that is true, then the probabilities say that the path is longer, whereas, sorry, that d is greater than, what's the constant that we should use in the end? Okay, let's leave it unspecified. A constant times log n for a large enough constant. That's the probability that our x is less or equal the magic bound. It cannot be more than this. But x is the sum of d random variables. So the expected value of x is 1/2 times d. And so you see if you put c large enough, then the expected value of x is much larger than this 1.35 log n. And so you can apply Chernoff to this. I don't know, maybe we pick 7 ln n. So it's 14, so it's twice as big. Just to make up some numbers. So you can apply Chernoff bound to something like this. Now, I'm shortcutting a long computation for 2 reasons. Maybe it's insightful if you try it yourself to figure out what constants can make this work. But there's one little catch that I glossed over and that you have to fix. Namely, these xi are not actually Bernoulli 1/2 random variables, and they're not actually independent. They're close to it, and you can fix it, but not exactly as I defined it. And the reason is intuitively easy to see in the picture. And it all comes just from stupid rounding issues. If you have a certain size n and you're trying to split this, you don't have exactly probability 1/2 that you fall between 1/4 and 3/4 with your pivot, because n may not be divisible by 4. And so the probability is not exactly 1/2. It's something close to that, but rounded to multiples of 1/n. It's got to be. But that also means the probability for this guy is not independent from the balancedness of the parent, because the way the parent chose its pivot influences my size. So there's a sneaky, tiny little dependence that sneaks in. Because the pivot ranks has to be a multiple of 1/n. Or the relative pivot rank, I guess. Let's say it has to be integral. So it's not, in the picture, I pretended that we have a uniform random variable at each level, and the truth is it's not exactly that. But the thing is, you can fix this by modifying your xi to be the combination of two events, that the pivot is in the middle, or if you know, because your size is not divisible by 4, that this won't exactly work, you add another option, you flip a coin with a small probability that offsets things so that, again, the combined event has exactly probability 1/2 to succeed, no matter what n of v is. I'm going to leave it here with this, because I think the details there are very quicksort specific and maybe not so exciting or general. But I found it cool that you can use the standard Chernoff bound by just applying some elementary clever tricks outside of it and use it for things where the exact assumptions are violated. As one concrete example, you can show that quicksort's height of the tree is greater or equal 42 log n out of all numbers, with a probability of order n to the minus 7.4. That's just what comes out of these numbers. There's actually even stronger statements about quicksort known. But standard Chernoff bound is enough to show with high probability in big O. And remember, that means the constant in front of the log n can depend on the exponent for the probability that you want. Okay, so that's all for this introductory part with all these models and formal definitions. We've seen already far back at the beginning of the unit that there's examples where randomization is strictly more powerful than anything deterministic. That was this example of selecting the median. We've seen a formal model for specifying exactly what randomized computation is, which is mostly useful if you think about complexity classes. So we'll come back to that. We won't have to talk about the Bernoulli probability space much, but it's there for you in case you want to have things formally defined. More importantly, we've looked at two types of randomized algorithms: Las Vegas, where we can never answer a wrong output, and Monte Carlo, where this is fine as long as it's most of the time the correct answer. And we've seen Chernoff bounds as the key tool to prove that independent repetitions are really very, very likely to give something close to the expected value of some random process.